How many are there?
19. Still 19.
19.
19. Okay, you can start. So welcome to the Professor Peraiah Foundation Award Ceremony 2021. Professor Anna Maneni Peraiah was an eminent theoretical astrophysicist and a faculty member of IAA from 1978 to 1997. He was a radiative transfer theorist who worked on a variety of topics in pure radiative transfer theory and also on its clever applications to novel astronomical problems. Professor Peraiah Foundation was set up in his memory. The foundation instituted the Professor Peraiah Foundation Award to recognize outstanding work in the field of theoretical astrophysics. This award is given every 2 years to a scientist working in India and below 60 years of age. The foundation has an MOU with IAA to organize and administer the award-related matters. The first award was given in 2019 to Professor Tirthankar Roy Chaudhary from NCRA, TIFR Pune, for his contributions in the field of galactic astronomy and cosmology. I would like to recall that the first award ceremony was held on 5th August 2019 and was coordinated mainly by Professor K.N. Nagendra and also by Professor K.E. Rangarajan. Sadly, we do not have Professor K.N. Nagendra with us today. He was also one of the foundation members. So today we have gathered here for the second award ceremony. We are joined by Mrs. Peraiah, who is the president of the foundation. I request our director, Professor Annapurni Subramaniam, to welcome her by presenting a bouquet. Thank you. We also have with us Professor N. Kameswara Rao and his wife, Professor K. Rangarajan and Professor M. Srinivasa Rao from the foundation. And Dr. Vagishwari, who is a foundation member, has joined the award ceremony remotely. And also Mrs. Peraiah's daughter, Usha Annamaneni, has joined remotely. So I welcome all of them to the ceremony. So from IAA, we have here with us our director, Professor Annapurni Subramaniam, our dean, Professor Ishwar Reddy, and senior faculty of the institute. On behalf of the foundation, I request Mrs. Peraiah to kindly present a welcome bouquet to our director. Thank you, Mrs. Peraiah. Most of the IAEA scientific staff and students have joined the ceremony remotely. I welcome all of them. I now request our director, Professor Annapurni Subramaniam, to present the welcome address.
Good afternoon, everyone. I welcome you all to this afternoon to this hybrid mode program of Professor Peraiah Foundation Award Ceremony. I'm glad that many of the foundation members could actually make it, and we're all glad that we're able to conduct this ceremony post the second wave of the COVID situation. And as you all know, the first award function was done 2 years back. That's the grand ceremony where many people could actually come and participate. And unfortunately, due to the events and the pandemic, people are not able to travel, and we are missing Professor Peraiah's children physically present here. And now on behalf of the Institute, I welcome you all to this function of faculty, students, and the awardee as well, and the foundation members to this meeting. So I was just remembering what all happened the last couple of years. We had a lot more faculty who knew Professor Peraiah quite well. Now we are seeing the generation change, and the number of people who are there in the audience knowing Professor Peraiah is reducing as well. So I thought I will talk a little more about how when I joined the Institute in 1990, got to know about Professor Peraiah, and he had a lot of students and the kind of activities, which actually kind of, though I was not working in that field, kind of motivated us to, perform well and be active. So that was something which we learned from people like Professor Peraiah then. Professor Peraiah joined IA as a reader on 24th of February 1978, and he became a senior professor later on in 1992 before he superannuated in the middle of 1997, and so he contributed about 20 years of service to IA. And during that period, I think I knew him from 90 onwards to 97, and whenever you discuss a point with him, there's a lot of clarity. The way they look at the problem and the way it's not like in nitty gritty.
Yeah, just you can take it forward. You can give it back in the evening.
The way now you look at it is kind of quite drilled and focused. So what happens is when you're looking at it in a broader sense, you will be able to take it to broader scales and broader applications as well. So things like that probably are reducing now, but I'm not sure. So he used to have a lot of students, a lot of discussions, and a lot of activities. And particularly theoretical physics, radiative transfer, we used to have a lot of people working on it. And right now, here physically present, we have Sampurna, and I think Sujan worked with him. Sujan was a student, and then he moved on to other topics as well. And we have Dr. Rao here and Rangarajan. So we are here with them. And as Sampurna was saying, we miss Professor Nagendra and this function, who actually did the first award ceremony. He conducted the whole ceremony then. And to talk about basic, how, where and all he studied, etc., just for the benefit of the new generation. Professor Peraiah did his MSc from Delhi University, and he did his PhD at the University of Oxford, England, and he joined IA in 1978. And he has a lot of publications, and he started his research career with the study of evolutionary aspects of binary stars and their atmospheric properties. He developed the solution of radiative transfer equation and spherical symmetry using the method of discrete space theory, and used it to solve a variety of transfer problems. Then there are a lot of other things which are there available. He applied this transfer problem to Compton scattering and computed the lines in dusty expanding spherical atmosphere, derived velocity profiles for stellar events in ONB type stars. So wide variety of applications, etc. He's given several lectures on stellar atmospheres at Bangalore University, stellar atmospheres and radio transfer in the Department of Astronomy and Space Sciences, Punjab University, Patiala, etc. And he guided several MPhil students and 12 PhD students. He also delivered a lot of lectures in different institutes and colleges. He had a wide research and academic experience. He was a lecturer in the Department of Astronomy, Osmania University from 62 to 66, lecturer in Northern College of Applied Arts and Technology, Department of Education, University of Toronto, Canada, 67 to 69, visiting fellow of the TATI for Bombay, 1971 to 73, and then in University of Heidelberg, 73 to 77, and in Netherlands in April to July 1976. His hobbies included gardening, listening to classical music, reading, and also driving. He shouldered several administrative responsibilities in IA, including the acting directorship in two short spells in 1991 and in 1992. He was the chairman of the group committee on theoretical astrophysics. He was a vice president of the Astronomical Society of India between 1992 to 1995, and he was a member of the organizing committee of Commission 36, International Astronomical Union, and also a member of the Indian Physics Association, Royal Astronomical Society London, Royal Astronomical Society of Canada, and the American Astronomical Society. So, he also has published a book, which is an introduction to radiative transfer methods and applications in astrophysics. And this is widely used as a teaching material, and this is one of the recommended books as a reference for the radiative transfer courses in many universities as well. With this, I think probably this kind of sets a stage for what kind of contribution he has made in the theoretical astrophysics here. And the foundation has come forward to set up this award, which is one of its kind for IA itself to have such a thing. So I really appreciate that and thank the foundation for doing this. And I hope that will bring more visibility to Peraiah's work as well as theoretical astrophysics to the entire community as well. I thank you all and welcome once again to this program.
Thank you, Professor Annapurni, for kindly giving the welcome address and describing the context of the program and Professor Peraiah's works and his at IU. So today is an appropriate occasion to remember Professor Peraiah, in whose memory this foundation and the award are instituted. So therefore, our next part of the ceremony is reminiscences about Professor A. Peraiah. I invite Professor N. Kameswara Rao, who is a foundation member, to present his reminiscences.
Thanks very much, Professor Sampurna and Professor Ramboni and the rest of my earlier colleagues. So it's a pleasure to be here and see that the second award is being given now, maintaining the continuity in spite of the COVID pandemic. And also as mentioned earlier, we very strongly miss Nagendra's presence here because he conducted so successfully last time. And he was a very, very sincere and well-reputed student of Dr. Peraiah. And my association with Professor Peraiah goes back to my student days when I was a student in the MSc at Osmania University. He just then came from Delhi after doing his master's there. as a lecturer. And he was fairly young. And though we come from villages, he comes from a small village in Andhra. And I also come from a small village in Andhra, which is both of our villages separated by about 20 miles. And funnily enough, we only met when I was a student to him. And though as a lecturer, he was very, I don't know, he used to fill up the boards with equations. His intense aptitude to display mathematics was much more boring than the rest of this thing. But I don't remember very well what he taught. But one of my seniors was reminding me that he did teach celestial mechanics that time, I believe. But more than his teaching, his behavior, he was so social and so exuberant. And he was a very lively person. So we used to move like friends. And his habits were he has very, very strong views, strong habits, and comes out very colorfully. So as though he used to live in Nizam Observatory quarters, which was made by quite campus. Every evening there is a bus which goes to campus. But instead, he used to come with us to Koti, another place, and there is a restaurant, very small restaurant, which used to sell this Mysore bhaji and mirchi bhaji, which was his favorite. So every day, almost he used to go there and eat this thing, and then take a bus from there to Amritsar. I mean, the why I'm saying this is very focused and selective and very intense in what he does. Well, of course, he taught us until 1967. He left to Toronto. He was, those days, he used to work on apsidal motion of binary systems. His guru, Kushwaha, was one of the main first persons to work on stellar models, interior models. He worked with, the famous Schwarzschilds. And he worked on massive stars, stellar structures, OB and B stars. One of the ways those days to check a internal constitutional configuration was to obtain a figure called absorption motion constant from the binary systems and see match with the theoretical calculus. And Peraiah inherited this kind of problem from Kushwaha and started pursuing that in Usmania. And Professor Abhyankar was a strong force in him to encourage him. Actually, Abhyankar was the one who taught him there. And he also was responsible for his going to Canada. Abhyankar was in David Navapa Observatory for about a year or something like that. And then when he came back, he suggested to Peraiah to go and do his PhD there. So when he went there, but David and Dunlop Observatory has a strong tradition for observational astronomy. And in heart of Toronto, there is a telescope. So that Peraiah was asked to go and observe there in the deep winter, in 4 feet of snow and so on. So which disillusioned him from doing observational astronomy. And he moved from there. As it is, he has strong interest in astrophysical, theoretical astrophysics. He moved to Oxford and made a name to himself doing so-called a special system of solving radiative transfer in various ways. And according to the bio sketch which Gilman wrote, his interest in astrophysics started when he was in Guntur AC College, I believe. And then to pursue astrophysics, there are only two places. One was Delhi University, where there's a strong tradition of Kothari and Kushwaha. And the other is Osmania, where the observational astronomy was the focus. So from there, he went to Toronto, he went to Oxford, and then to TIFR and various other places in Heidelberg and so on. He established himself as a major figure in radiative transfer techniques as well as in stellar atmospheres. So when he probably decided to come back, Babu asked him invited him to be here. And he started as mentioned earlier, as a kind of school of radiative transfer, though I wish we'd have done a much more comprehensive stellar atmospheric theory as such. But his legacy is those people whom I already mentioned, which is still being continued very actively and internationally established themselves as pioneers in the radiative transfer methods and polarization and so on and so forth. As to the respect which he demanded those days, I would like to show you, this is the first journal of astronomy astrophysics, which was started by the National Academy and Bapu in 1980. And the first paper, first two papers in this issue was by Professor Peraiah. And of course, this has many very distinguished people like S. Chandrasekhar, Radhakrishnan, Rad, Srinivasan, Contopoulos, Sidney Vandenberg, and so on and so forth, very famous names. So you can imagine the regard which he demanded. That with these few words, I would like to conclude my remembrances of Professor Peraiah. He was a very generous person, very hearty, very jovial, and he should be colorful way of speaking, particularly in Telugu, with all the native slangs and so on and so forth. So I would like to thank IIA for asking me to reminisce about Professor Peraiah. Thank you.
Thank you, Professor Kameswara Rao, for the reminiscences. I next request Professor M. Srinivasa Rao, who is the foundation member, to present his reminiscences.
Good afternoon to everyone. Thank you very much for inviting me first to the Foundation, Peraiah Foundation Group Committee. It is one of the best place where we can share the memories of him. I have a very long association with him, nearly more than 3.5 decades. And we worked on different problems in stellar atmospheres. My first paper in reflection effect phenomena, which is his favorite topic. In fact, we used to submit many papers, series of papers we published on the topic. Whenever we submit, we used to have very good review reports on the particular topic. In fact, my thesis is also connected to the close binary stars. Later, we worked on the line formation problems, where in the presence of dust in the medium, without presence, and compare those profiles, line profiles. And later, Compton scattering and all other problems also worked. We also worked with the colleagues, partial redistribution functions and polarization, integral operation technique, which he has used for the importance of finding out the aberration and reduction terms, radial transfer in 3D equation, etc. So many of different, he is very good in selecting the problems and applying the radial transfer. He was very simple and honest and very humorous person. Whenever office is required, he has shared the responsibilities in the different levels, from gardening to canteen to administration to stores to many of things. I think I remember there is a sports also on volleyball trophy on his name. It was given, he sponsored one or 2 years, I think. But he was not happy with the computer center is not a good view for his works. He was always interested in having a 24 hours computer center should run. That is what the main aim is. Because previously we were all used to go to Chennai for computing our codes. and he also used to accompany with us. That we will be getting some 3-4 hours of time, which is not sufficient. So he was not happy with that kind of, we were having TDC 316. Maybe you all may not be knowing, myself and he went to Hyderabad to compute is one of his ports in ECIL. Again, having TDC 316, we both went there. 2 or 3 days we worked there, and we find that that computer also is not working efficiently. It's not so good. Finally, one fine morning, he comes and says that I think we should acquire a Unix operating system, which I went and saw in Lucknow. We should get that. So at the time, I think Professor Rangarajan and all, they are working in Kavanu. We have a vaccine system, but still it is not 24 hours going and operating is very difficult to get. So he acquired that. And initially, he made a committee with Professor Rangarajan. Mohan Rao, there was one more student used to be there here. Baba Varghese, Mohin. These 3 people, 4 people. They used to run beyond the officers. So that some extent he is happy. And afterwards, he made it as a 24 hours to run the computer system. Later, whoever wants, they can use the thing and they can switch it off. That is the way it has been computer center brought up. Later, Spark 10 and all those Pentiums and all. He was very humorous, as I said. Students used to go as students. Whenever their scholarship, they wanted to increase. So he used to make fun, you people are getting more than what I am getting. What he does is, he takes his salary, basic DI he adds, he divides by family members. so always it comes as less than what. So like that, he very humorous, very funny way he makes it. Another important thing which I can share with you, in this area where he constructed, there is a floods are there during that time in 1890s. He did not come 1 or 2 days. I did not come because there was a lot of floods in our area. He said he made the boat, paper boats, and then to see which direction water is going. So that is the way he makes fun. He has enormous knowledge on European history, Indian history, politics. You name them anything. He will speak according to is what he knows thoroughly. He mesmerizes you like anything. Sometimes if you don't see him, we feel weak actually. We go to him, get energy, and then we work. That is the way we have maintained, or he maintained us, I don't know. But we are all very happy with him, having worked with him so many years. And finally, recently, I saw that Telangana government is they wanted to start one museum on PV Narasimha Rao. So when PV Narasimha Rao was the home HR minister, he went and he met Professor Peraiah in Heidelberg. I'm trying to get his picture to that museum, but I am not able to get the proper link. If office can share that.
Actually, Peraiah has the picture.
Yeah, I have the book. That photograph we want to send to them, but I am unable to get the contact of the Telangana government. If office or somebody can help, I think that is also one of the most good good effort. Thank you very much for giving this opportunity. I'm happy. We miss him a lot, but he is a very joyful person, as previously President Kameswara Rao told. Very nice, we miss him, but it happens that it is that he is not there, is not the thing, but his students are there, the grand students are there, his great grand students also there. That he has seen them in one of the occasions of meeting. He has seen them. Thank you very much for giving this opportunity.
Thank you, Professor M. Srinivasa Rao. I next invite Professor K. Rangarajan, who is a foundation member, to present his reminiscences.
First of all, I would like to thank Professor Annapurni, Director, and Sampurna to having given me the opportunity to talk about Professor Peraiah, which is a very favorite topic of mine, in the sense I was associated with him for many years, was one of his first students. He had first three students, myself, Dr. Professor Mohan Rao and Professor Nagendra. Three of us joined almost at the same time, around 1978. So Peraiah had a very unique way of guiding the students. He used to believe fully in freedom. He used to say that I'm not going to teach you any physics because you already done MSc physics. You should be knowing. I will. That way, initially it was a little tough. He used to give us only the publication papers. You just go through these papers and you find out the algorithm from the papers, and then you work out, and then that's the way you'll have to go about it. You'll have to develop by yourself. But that was a very good method of getting the students. There's no spoon feeding. That stood in time for us. I think he did that to almost everybody, all the students. And so this is his characteristic way of guiding the students. And the next thing is he was extremely honest. For example, I used his code partially, and then we wrote a paper, and then we wrote a paper, and then his name was the first author because we have used his code actually. But he said, no, don't put my name. I haven't contributed anything to this publication. If you still want it, you probably you can put me as the last author or some such thing. Such was his honesty. So he set a nice trend. He taught us just not only the science, but also the ethics and the honesty behind it. Okay, so that was second hallmark. And third is the Peraiah for him and also for Bapu. For them, the family, the house, the office, the students, and science, astronomy, everything is one single entity. That is, everything is integrated. So he used to invite us, invite the students as well as the colleagues, and many times we used to end up in Peraiah's house with smiling Mrs. Peraiah welcoming us and giving us all kinds of nice food and a lot of fun. And so that is the kind of cultural setup. He could do that. And he used to tell us why I haven't, I'm not guiding you in a formal way is because I was trained like that in Oxford by IP Grant. IP Grant met me only twice in my PhD career. That is first time when I joined, he came and gave me the problem. That is, you are going to solve the radiative transfer in spherical geometry in homogeneous atmosphere. So this is all, he told. And that was the first time, that was the one time he met. And the next time was when Peraiah had finished the thesis and he had to give it to him for reading. That's the second time he has met me. So that's all, So I am going to give a very similar kind of thing. You have to choose your problems. You have to be on your own. On your own. So that is a kind of, guidance. That was very, very good. It helped us later on in the years, and we could do certain things on our own. And another thing, at one point of time, Peraiah said, see, Bapu it has been asked by the council more publications from the institute. So where are the publications? He was asked, and so Bapu asked me to, where are the publications? So now that you people have joined, already 10 months are over. You have joined the institute in 1978, October. And now it's already 10 months over. Where are the, I mean, you have taken scholarship for 10 months. Where is the publication? Asked. And what all we knew was only the number of papers which he gave us to read and a program, of course. He gave us a program. Now, there is, we have to find a connection between the publications and the algorithm. We had to work out the algorithm. And then from that, the steps, and the program didn't have any comment cards because the program was written by him for himself. Okay. So, and that is a good thing since we had to learn everything by ourselves. So we could immediately, we were searching for some nice problems in astronomy, and then we could find this mean number of scatterings and mean escape probability of photons in spectral lines from spherical media. So that is a problem first we did, and that was sent to JAA for publication. And JAA was recently started at that time by Radhakrishnan and Bapu, and they wanted to set a very high standard. So they sent the paper to tough referees. Lucky, I mean, and we could get through. So, but that gave us a lot of confidence. And the freedom that he gave us, and also the confidence. And more than all these things, at one point of time, Nagendra could not submit the assignment problem, the coursework. And Bapu was very unhappy about that. And but Peraiah supported Nagendra quite well. He said, I mean, here is a person who will do very well, just to give him some more time. And then we told Bapu that Nagendra was going through a very tough time because his father was very ill. He was living in Malleswaram, and he had to be given oxygen cylinder in the night, his father. And then he used to cycle all the way 20 kilometers and come to institute. And it was telling on his health. And but I mean, the support what Professor Peraiah gave to Nagendra stood in time. Nagendra proved himself very well. He developed a beautiful group, one of the best groups in the world. All his students are writing very good papers, high impact journals and whatnot. So, what I would like to say is, when if your student is not doing that well, at some point of time, you try to find out why he is not doing it. Maybe there is some reason behind it. Give him some time and encourage him. I'm quite sure that you'll get a good, good dividends at the end. With that, I would like to close. Thank you.
Thank you, Professor K. Rangarajan. Our next part of the ceremony is the talk by the awardee, Professor Shravan Hanasoge. I request our director, Professor Annapurni Subramaniam, to kindly introduce the awardee.
We have Shravan Hanasoge here. He's currently at the Department of Astronomy and Physics at Tata Institute of Fundamental Research, TFR, Mumbai. Shravan did his BTech in aerospace engineering from the Indian Institute of Technology, Madras, Chennai, from 1998 to 2002. And then he did his MS in mechanical engineering at the Stanford University. And then he continued to do his PhD in mechanical engineering from 2004 to 2007. His dissertation topic was theoretical studies of wave propagation in the sun. It was the areas of study included numerical methods and solar seismology. After that, he continued as a postdoctoral research scholar at the Stanford University at the Hansen Experimental Physics Laboratory. And he was there for a year, 2007 to 2008. And then he moved to, I think it looks like a combined fellowship between Princeton and Princeton University Department of Sciences. Someone has to mute. Yeah, thanks. So this was from September 2009 to September 2011. And then he also continued as a research scholar, associate research scholar from 2008. I think the whole thing is between 2008 and 2013. And then he joined TIFR as a reader in November 2013. And then now he's an associate professor. His research interests include turbulent convection and dynamo action, machine learning, numerical methods, optimal control and inverse problems, helio and astroseismology, terrestrial and exploration seismology, etc. So I welcome Shravan, and I invite him to give this lecture. You can come first.
That's right. Yeah. Hi, thank you so much for this award. I'm very grateful that I was chosen, and I'm grateful for the opportunity to present some of the exciting work that my group and I have been working on for the last several years. So primarily my work is on stellar physics, solar and stellar physics. I was trained as a solar physicist, but now my area has expanded. Yeah, so I work on the, as I said, on the sun primarily, and then now I've expanded to study the stars as well. So let me begin a little bit by thanking all my collaborators over the past several years. Many of my students who've done quite a bit in contributing to this program, and who've now gone on to become postdocs, and still collaborate with some of them, and collaborators abroad as well. Okay, so let me begin by telling you a little bit. This is a sort of a broad talk. I won't get into too much, too much of the weeds, but I'll just broadly tell you what we do. So, the sun is, some might think is a pedestrian object. It's so close to us, and we understand it so well, certainly in comparison to many other things. But there's still, what I want to indicate is that there's still many truly fundamental things that we don't know about what's happening inside. So here, I think, is an instance. This movie captures many of the most one second, sorry. Yes, this movie captures all these fundamental things that we want to understand about the sun. So what you're seeing here is a continuum in white light continuum, a movie taken by the helioseismic and magnetic imager, which is an instrument, space-based instrument. It's observing a part of the sun. As you see, the sun is rotating, and you see that these black dots seem to be forming at the surface. So you see these black dots that are forming at the surface, and this is magnetic field. This is solar magnetism, and you see this cluster of magnetic fields on the sort of to the right of the screen, and then another cluster that seems to appear following it. And so these are sunspots, or magnetic active regions, as they're called. And one of the central problems that has continued to elude us is how these are formed, where they're formed. Can we say when they're going to emerge at the surface? What are the fundamental processes that govern the? So much of the physics, in fact, is concentrated in this one little movie that you're seeing here, and unpacking this into all of its constituent elements is still an outstanding challenge and a very interesting one at that. As you can see, our data are extraordinary. We have extremely high quality, very clean data, and so we can do quite a bit of analysis, and the hope is that we'll be able to understand some of these questions, the answers to some of these questions. So what are the governing fundamental processes? So one of the most important inferences that helioseismology, the seismology of the sun, which I'll briefly describe later, has given us is a picture of how the sun rotates. So this is sort of a 2D cut of the sun, through its rotation axis. This is the axis of rotation here. And you can see a slice, and you can see that this is the equator, this is the pole. The sun appears to rotate faster at the equator than at the pole, as you can see here. And it has these are rotations of, contours of constant rotation. And this axis in nanohertz, 453 nanohertz is about 26 days, 26 Earth days. So you can see that, there's definitely a gradient in rotation. This is an extraordinary measurement because of its precision and how well we know it and how it stood the test of time. But another reason why it's extraordinary is that it's a very non-trivial rotation profile. We don't know what set of factors are conspiring to create such a unique rotation profile. And it's a very robust profile in the sense that now observations of other stars appear to suggest that they also rotate, like main sequence stars. So there may be some greater sense of universality, that the equator is rotating faster than the poles in a variety of sun-like stars. And so what are these fundamental processes that appear to be common in all of the sun-like stars, the sun and its cousins? And this is very important for understanding how angular momentum is transported, how magnetism is generated and sustained in the sun. This is another topic. In fact, Rajguru, who's at IIA, works quite seriously on this particular topic. Is part of what generates this magnetism, we think, is this circulation called meridional flow or meridional circulation, where fluid moves from the equator to the pole and then comes back somewhere in the inside. And it's materially important to understand what this flow is, because that sets the time scale of the sun's magnetism, we think. So for instance, we know that the sun's magnetism reverses every 11 years. But, and while there are many, many theories, it's not to say that there aren't theories, but there is no convincing explanation as yet are fully supported with evidence that explains why 11 years is the time scale, and what roughly 11 years, a little bit here and there, but so this circulation, the time scale for a fluid element to complete this circle, this entire loop, is thought to be the source of this time scale. But whether there once in this particular image, you can see there are two cells. Rajguru gets one cell, so that's a very important distinction. And so this continues to be a very important problem. Convection is critical to maintaining all of the external solar phenomena that we see, including rotation, differential rotation, and so on. But convection is routinely known to be the least well understood aspect of stellar physics. The dynamical scales range from the radius of the star all the way to centimeters. So the huge spatiotemporal dynamic range, and understanding how this entire system is connected and simulating it is certainly not a solved problem. But we can image the interior of the sun and try to understand what's going on. So this is another important problem. And there's a recent, somewhat more recent problem. The Rossby waves, for instance, drive weather on Earth. They've been predicted by Gustav Rossby, I think, or Carl Rossby, I forget what his name was, but nearly 70 or 80 years ago. And they've been observed very clearly on Earth. But now recently they've been observed also in the sun. And remarkably, numerical simulations, a variety of numerical simulations are unable, or in fact don't show the presence of these types of Rossby waves. And so there's something fundamental that we're missing, some ingredient that's missing in convection or in the way the sun operates, which has more important consequences, not just the absence of Rossby waves in numerical simulations. That's not that's a smoking gun, we think, to some deeper, ingredient that we're missing. So there's many fundamental problems, very high quality observations, very solid constraints that we have. And so if you really think about all types of physics, you start off with some very coarse data, and then over time it becomes more precise. So, 1996 were the first ground-based observatories of the sun, continuous observations of the sun began. And now we have 24 years, 24 years now of nearly continuous data. And so what you can do with these data has obviously changed a lot with time. So we have much greater handle on precision and so on. And so the theories and the techniques to observe these, to analyze these data have also improved and with time and have gotten better. And so it's not just the sun with stars. We have all these now instruments observing thousands and tens of thousands and hundreds of thousands, and with Plato millions of stars. Maybe. So it's really quite an extraordinary data set that we can begin to work with. And, with all of these problems, you have to find an important niche that there is, so some unique niche that you can occupy. And so my particular focus is in marrying, techniques of computer science with important problems in these areas. And so there are many exciting problems, I think, on the forefront and the interface of these two areas. And so this is the question that we attempt to ask, have been attempting to ask: can we enhance our understanding of the sun and stars through better models, theory, and computing? So let me describe my bread and butter. So this is how I began as a solar physicist. It's just the seismology. So what is seismology? Well, seismology we routinely performed on the Earth as well. Is you have waves that are generated. I mean, all life is in some sense seismic. Seismic doesn't necessarily just need to mean acoustic, right? We see light and we form an image. Photons enter our eyes and we form an image of this room, for instance. So our brain is a very sophisticated seismometer. It's getting all this data and it's solving an inverse problem. And then you have all these theories. There are corners. There are lights. There are people. So you build a theory of what's going on here. And so in a very similar fashion, waves are excited in the Earth, for instance, by earthquakes, and then you use those waves to build a model of what's going on inside the Earth. And so there are sound waves, for instance, in the sun and stars. And so you can observe, in principle, you can use that to infer the properties of the interior. So here's a nice movie. This is taken by the Michelson Doppler imager. And if you squint and observe carefully, you can see a little bit of static at the center of this image. And so these are the normal modes of oscillation of the sun, basically. The period is roughly 5 minutes or 300 seconds, give or take a few millihertz, 3 millihertz, if you will. And these oscillations are observed and then decomposed into millions of normal modes. And so we observe them with great precision, as I've said earlier. And here's the physics of these modes. So they're excited at the surface, they propagate towards the interior, where the increasing sound speed sort of deflects them away from the center. And they oscillate in these cavities. And these are the normal modes. These, for instance, this normal mode is restricted to this region. This normal mode is restricted to this large cavity. And so the idea is you combine all of these normal modes and you can observe localized parts of the sun. You can add and subtract these signals from these modes. And then if you do it correctly, you know all the mathematics, you sort out all the systematical errors in the instrument. In principle, you can get a high quality 3D image of the interior. That's the dream at any rate. And we're still it's work in progress, but that's the idea. And so mathematically speaking, what we have is the measurement of the Doppler shift at the absorption line, the photosphere of the sun. And we measure that at all of these points, theta and phi. This is also phi, but latitude, longitude. And we then project that onto spherical harmonics and transform it into the temporal Fourier domain. So that gives us this quantity, which is the oscillation measured as a spherical harmonic angular degree L, azimuthal order M, and temporal frequency omega. Sorry, you can't see that.
So the deflection is because the density of the core.
No, it's the temperature. So if you think about it, the wave has a finite wavelength, and as the wave is propagating inside, for instance, here, one part of the wave is slightly deeper than the other part of the wave, which is slightly shallower. So the part of the wave that's deeper is moving slightly faster because the sound speed is greater. So it's deflected away. You see what's happening. So it's the temperature basically that's increasing. So the sound speed goes the square root of temperature, and the sound speed is increasing. So the part of the wave that's deeper is moving faster, causing the wave to move basically back into the surface. And so then at the surface, what happens is the density falls very rapidly, and that forms the upper boundary, and it can't oscillate beyond that layer. There's no actual boundary, right? And in the Earth, of course, you have an actual physical boundary, but you don't have an actual boundary. Okay, so yeah, so mathematically, it's a very beautiful idea. So all of seismology really is a study of the spectrum of the operator. So a spectrum of any operator, of any mathematical, you talk about a PDE or you could talk about a matrix, and its eigenvalues and eigenfunctions that basically form the spectrum. And typically what we think of when you think of seismology is, we think of resonant frequency, right? So you take a metal ball, you tap it, and you hear the frequency, and that's the eigenvalue of that system. And so from that frequency, you can tell the density of this medium. You can tell if it's a shallow ball, it's a hollow ball, is it a solid ball, is it like water? I don't know. So various things you can say about it, right? And the more balls you listen to, maybe the more discerning you become as a way of telling these things apart. Those are eigenvalues. That makes intuitive sense. We can also use eigenfunctions, which make much less intuitive sense, but are also a very powerful way of actually, and eigenfunctions are measured at the surface. So you can measure the vibrations of this ball, for instance. And those eigenfunctions can tell you what's going on in the structure. So let me explain the principle here. So you start with the reference model, which is a very simple model of the sun, but very sophisticated in other ways. So it's non-rotating, it has all of these attributes. Quote unquote simple, but it retains the stratification, the density, the sound speed. It's able to largely predict all of these correctly. And then you have the sun itself, which is of course a far more complicated system than this reference model it can hope to aspire. But what is actually amazing about all of this is, sometimes it's really quite amazing that the reference model is actually just a small perturbation away from the sun. And so you can take this model and you can perturb it in the framework of linear perturbation, a small perturbation theory, which I think is quite remarkable considering how complicated this system is in comparison to this. Okay, so now we know that for waves in the sun, linear theory works extremely well in small amplitude linear waves. And the reason we know this is that we measure those eigenfrequencies of these modes, of these millions of modes, extremely precisely. And this reference model you can predict all the eigenvalues of this reference model. And it turns out that eigenvalues that you measure are very close to the observed normal mode frequencies of the sun, within a few parts of 1,000, in fact. So that level of precision tells you that something has got to be working right. And so we assume that linear theory generally is a good framework with which to model this. So now you have the mathematical elements, the building blocks forming, right? So you have a nice linear wave equation on a 1D reference model. And so this immediately tells you that if you study the operator a little more carefully, it's self-adjoint, which means that the eigenfunctions of this operator are orthonormal complete. So every eigenfunction of the sun, in principle, can be expressed as a linear combination of these eigenfunctions. And so this principle, which was first broadly thought through in quantum mechanics and has been used by terrestrial seismologists next and now by us, is the fundamental guiding principle of what I'm going to tell you about, what my group has been working on for the last few years. That every eigenfunction of the sun is a linear combination of the reference eigenfunctions weighted by these coupling coefficients, these alpha k, k prime, which tells you every kth eigenvalue of the sun has some, constant coupling constant of k prime eigenfunction of the reference model. And if you can measure these coupling coefficients, alpha k, k prime, which we've figured out how to do, I won't describe the mathematics any further, but this we can measure. And then once you measure this, you can build a nice inverse problem that tells you how to go from the reference model to the sun. And then you build a 3D image. As I said, that's the dream, right? So we're still working on the dream, but that will make it possible, in fact, to achieve this. So my group has been working, or some people in my group rather, have had a laser focus on this thing called normal mode coupling, this technique called normal mode coupling. And I'll describe the program to you at the end, what we're thinking about this and problems in which that we're attempting. Let me just briefly describe why it's proven to be much more extraordinary than we had originally imagined. This is actually the biggest thing that we've discovered this years later, that it has a signal to noise that is an order of magnitude higher than other comparable methods, at least a method known as time distance. And that order of magnitude is just impossible to conceive of, because we thought we were squeezing everything out of this seismology. So the fact that we're using this mode coupling means that we're using all the seismic information there is, and that's giving us presumably much higher signal to noise. So this is the most crucial thing. The next thing, which only practitioners will perhaps know, is that spatial window, we can only observe half the sun, and that causes spatial leakage. So you can't isolate the spherical harmonics completely, right? It's the Heisenberg principle. You window in space and you expand in the Fourier domain, right? So it broadens in the Fourier domain. You lose that ability to focus, and so that creates what is known as leakage repetition. You have these features repeating. It's a technical issue, but the repetition with mode coupling it doesn't happen the same way, and it happens in a way that makes measuring things much easier. So the repetition window for practitioners is double the repetition window that you get for time distance or ring diagrams, which is another very remarkable feature, actually. And then there's other stuff. We can take all of the systematical biases very, very elegantly into this, folded into the theory quite neatly. It can deal with time-varying perturbation theory. So the sun is evolving dynamically, and so that's again quite a nice thing. In terms of data manipulation, it's remarkably simple. We just directly there's a pipeline of data that's coming from the instrument, and we can just take that and produce these coupling coefficient measurements very easily. The theory is very, very well developed for this. And so the method now has been validated. We've been working on a lot of this stuff. It's a relatively new method. And so we've worked on validating it on a variety of standard candles, if you will, in helioseismology. So the method is ripe for actually making really, we think, remarkable. It's already made. In fact, I'll briefly describe what we've done. So this is the paper that I worked on last. Been working on a particular topic. I've been working on for several years, is to image the flow, convective flow. So how is convection in the sun? As I told you, it's one of the least understood aspects of the sun. There's a lot of things going on. The parameters that govern turbulence in the sun are in such an extreme astrophysical regime that we have no ability to say from theories on Earth, laboratory experiments or theory or numerical simulations, we have no handle on what's going on. So we have to look at observations basically to see what's going on. Here is a cutting edge, one example of a cutting edge numerical simulation, these two. And this is v theta, which is the latitudinal velocity. This is v phi, which is the longitudinal velocity of convection. And this is in Malvidi projection for those of you who know it. This is from direct measurements from the instrument HMI, seismic inferences. And you can see remarkably they're very different. So first of all, you can see that in the sun, convective flows are concentrated close to the equator. In the simulations, they're in fact diminished to the equator and they're higher at higher latitudes. There are a variety of other things here that I can point out. The scales are much smaller here than they're much bigger scales here. There are many other differences. Basically, in this paper, we showed that there are some very fundamental ingredients that are missing in numerical simulations, and we have quite a long way to go, we think, from here to here. How do we take these simulations to understand the sun better? So that was one of the things we were able to achieve with mode coupling. Here's a problem in which I'm very excited, and I believe this dramatically improved signal to noise can afford us the ability to finally potentially measure G modes. G modes have been long sought after in the sun. And these are internal gravity mode oscillations, which are trapped inside the radiative core, as you can see here. And these P modes, which are the surface acoustic modes, they go everywhere. But these G modes, they decay from here to the surface. And so the question is, can we measure these G modes? And I think the answer is, with this method, if we tuned it, I think we can potentially make these first measurements because we're getting hugely improved signal to noise. Okay, so that's a first half of my talk. And it's basically seismology. And now I want to go into a parallel topic with a different method. I've divided this, as you can see, based on method, but the ultimate goal in all of this is to find new physics. And so in this case, I want to say why machine learning is such an important topic. So, at least with the sun, it's not the case with everything. We have enormous amounts of data from numerous different missions. So there's a lot of data. Not all of these data are useful. There's a lot of repetition, redundancy, and so on. But nevertheless, there's this potential to use and combine these data in a way that other contemporary methods cannot do. It's simply not trained because they're very different data. Some have images, some have numbers. So you can, in principle, combine all of these with machine learning. And so they provide a very powerful way to utilize these things. And as I was telling you, the movie that you saw earlier, this emergence of a new magnetic field is a very important problem. And so can we try to say something new about what's going on in the physics? Are there changes around in the sun just before a new magnetic field emerges to the surface? And so one thing to keep in mind is numerical simulations of the sun, which are very sophisticated and very expensive, are still strongly biased in some way because they're attempting to solve the equations may be correct, but in a regime that is very different from the sun. But machine learning, what you do is you assimilate the data itself. Your data is the fundamental product, right, that you're using. And so you're building a model out of the data, which then the hope is if you do this very carefully, you might be able to extract, at least it's not as biased as a numerical simulation in some ways. You could bias it if you're not careful with the data. And so that's one of the most important things with machines is that you have to be extremely careful with how you handle the data. Okay, so this is what I want to describe here. That machines appear to do much better in predicting, for instance, when the sun will flare or when new magnetic field will emerge and stuff. And so how is the machine doing this? I mean, you can use this as a predictive tool. We haven't attempted to do that. What we're interested in doing is trying to find out and unpack the machine. What has it found? And how is it able to achieve this performance? So here's a movie of a flare, for instance, and so you can see that there's violent magnetic. There's reconnection here, and there's the violent magnetic event, and plasma is being hurled out to the sun. And this has, of course, material consequences if you're on Earth. Satellites, people, I mean, everyone knows space weather and so on. So it's very important. And so, for instance, this is a flare, and understanding what leads to this, what things have changed around here that lead to this is super interesting as a physics problem, and what's going on there. Of course, also important as trying to say, to predict when the flare will happen, but certainly in physics. So we trained a machine a few years ago to try to look at these data. And these are for very large energy flares, X-class flares as they're called, which produce a fair amount of X-ray luminosity. When they X and M is one level, one magnitude lower, but there's a huge amount of flux. And what this machine seems to suggest here on the horizontal axis is the time. 0 is when the flare happens. And this is pre-flare, this is post-flare, as you can see. And this machine is telling you whether this magnetic region is going to flare or not, just like the one that you saw in the movie about a minute ago. And so what this seems to suggest very remarkably is that these magnetic regions, they're, well before the flare, they climb into some state where they're ready, they're flare ready. They're ready to flare for days, it seems like, even before or after. And then when this current helicity, which is another, it's measuring the type of current density in that magnetic region, seems to rise sharply when it gets to t equal to 0 and then sort of diffuse later. So there are these very important signals that this is, and so machine learning, with this machine learning, we were able to discover these things. And so if you use machines carefully, you can discover statistically important physical processes that are occurring, which these were not known before. It's just if you train the machine well and you ask why the machine is predicting this physics, then you might be able to say something new. So this is of particular relevance. I wanted to show this to IAA. And I want to thank B. Ravindra, who had given me the calcium K and the H alpha Kodaikanal data. There's 100 years of archival data. And now, we ask ourselves, what can we do with 100 years of magnetograms? This is not magnetogram data. But if you had 100 years of magnetograms, can we do some new physics? Can we say something new? And so we devised a machine. It's a semi-supervised machine. It's a generator discriminator. I won't really get into the details, but actually, I want to briefly describe what the machine is. It's interesting. So this is one of the images from the Kodaikanal Observatory, calcium K, goes into a generator. What the generator does is it sees an image like this, and it creates a magnetogram. It happens over a process of training, but I'm just giving you the answers. It creates a magnetogram from this calcium K. And here's an observed MDI image of the same time. This is the true, this is the fake is reconstructed magnetogram because we don't have this datum. And then the discriminator tells us whether this is a good representation of this and this are reasonably close. So it's basically comparing this with this and this. And then it gives you broadly some indicator saying, yes, it's a good image or it's not such a good image. And it continuously improves. And then over this process of iteration, you train the machine over some time. And then it learns how to take the calcium K data and then reconstruct a magnetogram. And so now we have 100 years of magnetograms, actually. We're writing a paper on this topic. And so here is these two huge storms that happened, 2003 Halloween storms, huge X-ray flux, very big storm. 1989, it took out the Quebec, it took out a power station in Quebec, and there was widespread loss of electricity in Canada, so some parts of Canada at least. And so here, for instance, is the Kodaikanal Observatory calcium K image. Here's Kitt Peak, which was also taking magnetograms at the time. And here's a reconstructed image. It's if you look at it closely, I'm showing it to you from afar, but the reconstruction is quite good. It's able to get the magnitudes right. It's able to transform this calcium K and able to, even in some cases, get the sign of the magnetic field, which is remarkable because calcium K doesn't really contain sign information. So now we're trying to ask other questions about with the magnetograms. Here is a 100-year-long butterfly diagram. This is an accurate thing. There's no issue. We can go right up to the poles, and no one has these data before. And we only have these beautiful data because of the Kodaikanal guys who kept this observatory running for 100 years. Or now it's over 100 years. But it's a super synoptic map, which is basically taking the equatorial magnetic field and you place in some I don't want to describe this, but here is Kitt Peak, which is taking these synoptic observations for the last nearly 50 years, and then here's a reconstruction of it. It's pretty good. It's pretty good. So we're still improving it a little bit, but we can ask a lot of really nice questions once you have these magnetogram data. Okay, so I'm starting to get to one of the last topics, and then I'm done. So what can we do with stars? So this is all about the sun. I'm focused on the sun And now I'll talk a little bit about what we can say about stars. So all stars oscillate, so it's just a question of whether you can observe them or not. So most stars are very far away, or they're very faint, etc., etc. And so there's only a few stars that you can actually observe. And some stars have extremely complicated oscillation spectra. Some stars have very simple spectra. Some stars we understand, and so on. So there's a full range here. And there's all these missions that have been launched, and once Plato is yet to be launched. And they're all going to observe or have observed. So all of these have observed hundreds of thousands of stars in the hope they're planet hunting missions. But we have high quality observations of these stars, right? And so these current algorithms that we have to study these oscillation spectra are just really expensive because they use MCMC, which those of you who know take a long time. They require a lot of human intervention. You need to pay attention. Works if you have a few hundred stars, maybe a few thousand stars. But when you're starting to get into 10 to the 5 and 10 to the 6, it's not sustainable anymore. And so if you really want to do ensemble stellar physics and test the hypothesis of stellar evolution and understand this, you need an algorithmic revolution. You need to transform the algorithm to something that can handle such vast data without losing accuracy and produce results for you very fast, basically. And so machine learning, we've demonstrated, is in fact that silver bullet. It seems to do everything. So here it is. Here's the idea, right? So we have a theory of stellar evolution or stellar pulsations. We know how stars oscillate. We certainly know how the sun oscillates. We know how sun-like stars oscillate. We know now how red giants oscillate. We know how other stars, like Gamma Doradus, there's a whole class of stars that we know. And there's a few parameters that govern the oscillation spectra. So where are for instance, in the sun, where are the resonant modes? And where will they be? And to what parameters are they connected? And so we know this theory very well. It's actually a really nice, elegant theory. So we can go very nicely, very quickly, in fact, from the parameters. There's a few parameters, like 10, a handful of parameters. And you can produce nice oscillation spectra that look like stellar spectra. And it wouldn't exactly be stellar spectra because the noise is different, et cetera, et cetera. There'll be some other, small differences, but broadly, these are the you can go this way. This is the forward problem. But the other way around is what I said was very, very expensive. So if I observe an oscillation spectra, if I say, what are the parameters that govern the spectrum? It's very difficult to do. This is the part that I said is unsustainably expensive and requires a lot of human intervention. 3 hours or 4 hours, I'll describe the numbers actually. So this is what machine learning does. It enables this inverse problem, if you will, while maintaining accuracy. It accelerates it by many orders in magnitude and speed. Okay, so we tested on red giants and explain a little bit about why that's the case. As stars age and approach their subgiant and red giant and clump phases, their oscillation physics changes. So main sequence. So as a telltale sign of the star's evolution is its change of oscillations. That's how we're able to connect oscillation spectra to the properties of the star. And one of the things that happens is as the star becomes larger and larger, which is what happens when a main sequence star is. And first of all, just to say, the sun's oscillations at this range. If you observe the sun as a star, it's a little dot. You could only see the largest of the global nodes. Right? The entire star has to be oscillating. So you can only see very, very low degree oscillations of the sun. Are extremely easy, very, very simple to predict. And any person could just look at the spectrum and understand very quickly what's going on. But as the star evolves, as the main sequence star evolves, it becomes larger and larger. Its acoustic frequency and Brunt-Weisler frequency, which is to do with internal gravity modes, they start to become closer and closer. and acoustic cutoff frequency drops. Anyway, there's some other some complicated physics going on. And so then what happens is very remarkably, and this was not known until a decade ago. It was in fact just a very remarkable detection that happened as I said, with Kepler. So you have the core of the red giant, and then you have the envelope, and you have the acoustic modes that are sitting in the envelope, and you have these G modes, these gravity modes. You remember I showed you an image about how in the sun we're trying to detect these G modes for decades, but we haven't been able to see them. What happens is, as the star becomes older and older, these acoustic modes couple with the gravity modes in the interior, and then you suddenly have this new magical mode that samples both the very deepest interior of the red giant and the external envelope. And suddenly you have constraints now. You're peering into the very heart of the star. You have constraints in the rotation, structure, density, all of these properties in the deepest inner core as well as in the envelope. And so you see here in this image, the blue line, as you can see, all of these, is our theory. That is this part of it, the forward part from the stellar parameters. I'm generating an oscillation spectrum, and the black lines that are from KIC 6191190, so actual observations of a red giant. And you can see that the blue lines are very accurate. And if you look really closely, they actually get almost all of these peaks. These peaks are oscillation peaks, all of these. And so you can see in the spectrum, sorry, I forgot to explain the spectrum. The horizontal axis is frequency in microhertz, and this is in ppm squared per microhertz. This is basically the oscillator from the light curve. You can produce these oscillation spectra, and so you see these two lines here. See these two lines here. You see these. These are the main sequence, simple main sequence oscillation frequencies. They're much simpler, right? They're just two lines, two lines, two lines. And then you see this forest of peaks here in the center. This is the stuff. This is the mode that's going deep into the core and coming back up to the surface and the whole thing. And so this is much, much more complicated. As I said, mode identification becomes very challenging in these modes. And so these are very difficult to go the other way around. I can predict them, but if I knew all the parameters, but once I observe the oscillation spectrum, I don't know what created these spectra. And so we trained a machine with millions of these spectra. It's not taken very long. It takes a week to train the whole thing, and the machine itself is complicated. The machine took us the architecture of this machine took us a year and something to arrive at. It has for those of you who know, it has a convolutional neural network followed by an LSTM. I believe there's another layer, a couple of layers there. So it's a complicated machine, but it's in the end. So it works. So what I want to show you are the stellar parameters. There's a delta nu. I don't need to explain it. I'll explain it actually in the next slide. And there's another parameter, delta pi. These are the two broad parameters that govern the structure of red giants. And here on the x-axis is published, and for stars that we know already, that have already been analyzed. And here is the predicted. And you can see that first of all, our predictions and the published values are just incredible for this delta nu. They're just right on. They're within a percent, I think. The delta pi is a little bit more storied. You can see there's a few points that are off the axis, but it's misleading because the very high density of points are sitting on this line. So we're able to predict these things with very high accuracy. And some of the stuff that's off this line may actually even need to be revised. And so not fully clear who's right in that. It's something that we'll do at some future point. But I want to. Yeah, it's a red giant.
So the prediction is based on stellar parameters.
So we take the oscillation spectra. So first we take a machine. We generate these synthetics, millions of synthetics, like this blue lines here.
Because your R delta pi,
yeah,
delta nu changes as we move up. So
yeah, I just showed the next slide. I'll just explain that. Yeah. So first of all, we're able to, for all of these stars, at least for the known stars that have already been analyzed, we're able to recover exactly what has been independently achieved through a much more expensive computational method. And each star takes less than a microsecond, in about 2 to 3 hours for that same star with significant human intervention for MCMC. So we're talking about 6 + 3, 9 to 10 orders of magnitude speed up. It ceases to be interesting. I mean, once you cross a couple of orders in magnitude, it doesn't matter anymore, but it's super fast and highly accurate is the point. And so this is the thing that you were saying. And so when we train this machine, there is an intrinsic delta nu, delta pi correlation for red giants. And the delta nu that I showed you in the previous slide has to do with the size of the envelope. As delta nu reduces, its envelope is decreasing, is decreasing. Whereas when delta pi increases, the core size is increasing. So there's some competition between these. And there is this, you can see there's an intrinsic relationship here. But this is from our machine. But when people typically do this analysis with MCMC and so on, they assume already that delta nu and delta pi are correlated. And they know this from a few samples of stars. In theory, they know that this is correlated, and they use that as in fact a bias, right? But we don't bias it. When we train the machine, we're saying delta nu can be randomly selected over this range. Delta pi for the star can be randomly selected over this range. And we create millions of synthetic examples. We train the machine on these examples because it's a synthetic. So I know what the delta nu and the delta pi are. So the machine learns these delta nus and delta pi's. There's no intrinsic correlation in the training data set. I am not imposing this correlation. And then I apply it on data, and then this thing beautifully emerges, exactly as it should be. So, all is well so far. So we have lots of new inferences. We have inferences about rotation, which I'm not showing here. It's still work in progress, but we already inferred rotation. We've inferred changes in core size as unexpected changes in core size when, as these red giants evolve. Inclination angles of rotation, which are all extremely important in the context of angular momentum transport in stars. So our ultimate goal is what new physics can we really add to this, right? So there's a number of results that we're hopefully going to arrive at soon. So as I'll close with two things. I want to say a program, think of a program, a research program, if you will, of what my group and I have and will do. And so here is mode coupling, which, as I said, I've really taken to, and I think will displace or perhaps become the single most important helioseismic method, given its many powerful properties. And so I'll just go through some of the stuff that we've already done. There's a lot of technique development in the global case. We understand the full sun. And so we're doing a lot of work on Rossby waves. We've tried to image and we'll continue to image convection in the interior. There are these high frequency inertial waves that we've discovered, which we think lead to very remarkable new physics that conventional hydrodynamics can't explain. So we've a very clean discovery of these high frequency inertial oscillation modes of the sun. So I told you how important meridional circulation was. And so this, with improved signal to noise, can give us fresh insight into what's going on in the deep interior of the sun, I think better than what potentially other techniques. There's this G mode search, which is we're yet to initialize, but I hope we'll do soon. And far side imaging, understanding what the far side of the sun looks like, so you can predict when sunspots are going to, run around. We can see, of course, the near side of the sun, but before sunspots rotate onto the near side, you can image them using seismology. And so that's, we believe we can do it with this much better than other methods. Again, but it's still work in progress. And that's the global case. In the local case, we're trying to do this. This is the holy grail problem. Can we say something about magnetic field before it comes to the surface? Are there disturbances? Can we predict them? Are there precursors and so on? There's another scale of convection called supergranulation, which I didn't have time to get into here. So that's that. And then with the penultimate slide, I guess this is the ultimate slide rather, where with this machine learning stuff, there's a solar case where we try to do direct physics. We've worked on flares. We've worked on solar wind. Emerging active regions, can we say something, as I said before these magnetic fields emerge, can we say something about them? Expanding archival data, I told you about Kodaikanal and how interesting hopefully that's going to be. We know that we can rebuild the far side magnetic field just by knowing the near side field. So we've already seen some confirmation of this, which helps us double the amount of magnetogram data that we have over the past century. So we think we can do this. And in the stellar case, we've sort of already solved the red giant structure in some ways. That's solved it with achieved significant progress, where rotation is also kind of done, but we're sort of finalizing it. And we're in the process of applying it to Rho AP stars, Delta Scuti, Gamma Doradus, all these interesting stars that have all these unusual rapid rotators, unusual physics, and so on. So that's it. Thank you. Thank you very much.
Thank you, Shravan, for a very interesting talk. Sorry, there was some disturbances there. Okay, so I invite questions from the attendees. In the chat box, there's a question already from Professor Taria. You can unmute and ask. Professor Taria, you can unmute and ask. Okay, so I'll read her question. I note that according to the machine, there seems to be no clear change in the magnetic activity immediately pre and post flare. Why is that?
I mean, this particular. There is a change. This one shows the current helicity pre and post flare changing, so it rises and then collapses. This is not magnetic activity. It's a different. It's actually it's what the machine thinks the magnetic region is going to do. The question we're asking here is this magnetic region going to flare or not? So it's a yes or no. So numbers that are closer to 1 means yes, it'll flare. 0 means it won't flare. And so you can see that it's in this state of being close to flare for many days. So it's not to say that the magnetic field, in fact, is changing dramatically over these few days.
I see.
Okay.
Yeah.
Can I just ask one more question before you move on? You're talking about stellar seismology. I was wondering how precise are the measurements of stellar oscillations to merit the kind of theoretical and numerical precision that you are putting into your machine learning?
Extremely precise. We know stellar oscillations. We measure with extreme precision. With these space-based instruments take extremely high quality measurements. So these oscillations are known very precisely.
So the oscillations you're referring to are the variations of luminosity with, basically you're looking at the light curves?
Yeah, exactly. So you measure the light curve and they're measured, I think the error bars in those are much smaller than the oscillation magnitudes that I show here.
Yeah, there is some question about whether the oscillations are entirely due to the changing radius of the star or whether it could be because of some sort of oscillatory conversion of hydrogen ionization states.
No, I think
resolved?
Two very different time scales. These oscillations that I'm referring to are in the order of minutes.
Okay.
Or, like this is 120 microhertz, which is
I see.
It's like an hour maybe, not less than 30 minutes.
Okay.
Yeah.
Well,
so
others of the means.
Yeah.
Okay. Thanks. Thank you.
Precision.
Is the differential rotation of the sun has any effect in the stratification of elements, particularly lithium? Because it is almost 2 orders of magnitude less.
Yeah.
The sun.
Yeah, that's a good question.
What it comes from.
Yeah, so a very good question. In fact, this is a debate, active debate, in fact, between Arnab Rai Chaudhary and a group in the US. Arnab believes that what actually transports it is meridional circulation. And so that is, my apologies, that is this circulation. So if this circulation, this dashed line is the base of the convection zone, where the temperature is about 1 million Kelvin. And so if this cell were to go inside deeper into the radiative interior, it would drag lithium down, and where it would undergo burning. The lithium would be burnt here because this is higher temperature lithium is unstable in this region. So in fact, one of the I think cases for meridional circulation to penetrate into the radiative interior is that the lithium depletion. In fact, sorry, I take that back. The reason why the group in the US, Peter Gilman and others, argue that meridional circulation cannot go into the radiative interior is that it would result in anomalous lithium depletion. And so it's not differential rotation, but meridional circulation that can transport it. But Arnab Rai Chaudhary and Dibendra Nandi, I don't know if Dibendra Nandi's position at the moment, I don't actually know what they think about this, but they have suggested that the meridional circulation actually goes inside the radiative interior. So there's some discussion about lithium depletion based on this.
I don't know about the sun, but in our red giants, the meridional circulation deplete a significant amount of lithium, but then this is still a problem.
Yeah, it is.
Why is so low?
That's right.
So another one is gravity modes. Is it because of sensitivity we are unable to do on main sequence stars gravity modes?
Yeah, it's about
There's
the
a new one plateau.
yeah. So what it has to do is the convection zone. So here is convectively unstable. Typically, main sequence stars have an inner radiative zone and outer convective envelope.
That's only less than 1.3. Beyond that, it will change.
Sorry.
Beyond 1.3
Right.
solar mass, it will be Uta.
Oh, that way. Yes, that's right. Yeah. So, but in this case, in the sun and it's comparable masses, basically what's happening is that these G modes become evanescent. They can't oscillate in this region, and so they decay. In fact, by the time they get to the surface, their amplitudes are very, very weak. It's a bit like these are trapped inside. These G modes are trapped inside, so they have a very faint signal outside.
But their amplitude is a function of stellar core density. For example, when you go to RGB stars, you see the G modes. There are few G modes and then there are mix of G modes.
Yeah, exactly right. Exactly.
So, but those are identified in some other spectrum.
Yes, that's right. Yeah, so
that's related.
Yeah, so it's very interesting physics. It has to do with there are these two parameters, the Brunt-Weisler frequency and the acoustic Lamb frequency, which tell you the difference basically between acoustic mode frequencies and G mode frequencies. And what happens in red giants is that these two become very close to each other, G mode frequencies and the P mode frequencies. So they start talking to each other. So the mode is no longer pure mode in some sense. It's a combined coupled mode between the P and the G. And so the mixed modes, for instance, is an instance where
frequency can start speaking.
That
is to do with central core density.
No, it doesn't have to. I mean, yeah. Why the yes? It may have something to do because it has to do with the yes. It may have something to do with it. Yes, because the Brunt-Weisler
concentrated most of the mass in the core.
Right. That and the fact that the envelope is expands means the frequency is reduced. Yes, it has to do with the structure of the star. In fact, you're exactly right. Yes.
Yeah, please.
So coming to continuation with that, so I was thinking that will you be able to understand the size of the core in red giants?
Yeah. So that was one of the results that I've not described here. But there's a coupling factor that connects to the size of the core. How much the G modes couple with the P modes depends on how big the core is. And when the core becomes very small, the coupling becomes very, very, very weak.
So that has got a very high implication on the convection in the core for stars which are these are convective envelopes.
That's right.
And radiative cores, but beyond 1.3, we're not able to exactly say where exactly the convection starts in the core.
Right.
And then the core also has a overshoot, convective overshoot, which actually has an implication on the ages of stars on the main sequence.
Right.
So if you are able to understand or measure the core mass, you can actually say that how much of convective overshoot has happened, and it just got an impact on how much is the age of those stars.
So basically one of the results is that we can measure core size. The core sizes seem to be dropping dramatically in a lot of red giants, much smaller than predicted by other methods. And so we're sort of testing this result. So it's very good to know this particular implication.
Convective overshoot, which actually starts from 1.2 and ramps up to 1.5.
I see. Okay.
And then there's a drastic change in 1990s when the previous models were called classical models. And then overshoot models
was incorporated and then it changed. I see.
Geneva group and Padova group incorporated the overshoot in the thing. But we're still not able to figure out exactly how much is the overshoot.
Okay.
Is 25% or 30%?
I'll be in touch with you then once we have some results then.
Wouldn't that depend on the chemical composition gradient of the corpus?
So not chemical gradient as much as the density that controls the oscillation frequency. When it's very, very dense, it has implications on what frequencies of G modes you have there. So chemical composition does affect it. You're right. There is a parameter, but typically that parameter doesn't change as much as the density can, which can much more significantly affect the oscillation frequencies.
If you have a companion, how would this?
Yeah, so that's also very interesting. With some of these things, they create tides. So you have inertial oscillations. That's that change that it's in a different part of the spectrum. You have that. But in fact, there are companion red giants where you have two red giant oscillation spectra that are sitting right on top of each other. Or red giant, no, we have actually, sorry, let me take that back. We don't necessarily observe red giant companions, but rather red giants with a main sequence star or some other type of star. And so if the frequencies are similar, they're sort of superimposed. So you're seeing a combination of light from both of these. Yeah, so that's one of the things. In principle, you can. But somehow it doesn't seem like the most important physics question. Like I don't know what dramatic new physics we'd get, but it's certainly an interesting question.
The light have you seen the spectroscopic light variations?
No, I haven't. I haven't focused on that type of work.
So different lines.
Yeah, we haven't looked at that type of stuff. That for the sun, you can do a lot of really interesting things by looking at different atmospheric heights and so on. That provides independent information in different layers. I believe Rajguru's group also does that here at IAA. But something, and others do it. Dipankar does it. I'm sure others do it here as well. But yeah, that's something that we can later on we will think of incorporating.
Okay. There are two raised hands. I request to ask very briefly only. Jayant?
Yes. So I want you showed the HMI measurement of the confinement of the convective flows. And yeah, exactly. So you see that the equatorial preferences, what is the physics behind it? Means why you see, and what depth it is actually?
This one is at 0.995. This is very close to the surface, in fact. Large scale flows. Look, I don't I can speculate, and I'll offer you a very, I think, respectable speculation, but we don't know what the physics is. But the speculation is that we have differential rotation in the sun. So if these convective features were actually elongated, then the fact that the equator is rotating faster than the pole will mean that it'll get sheared out. So it'll lose structure, and because this thing is shear, you have continuous. So the low latitudes are rotating faster than the high latitudes. So if you had long elongated structures, they wouldn't last. They would just get sheared away. And so these things are trapped within the equatorial rotation region. That's my speculation, if you ask me. But we don't know if this is exactly. We don't know if it's true or not.
Yeah, thank you. If may I ask a very short question? So using the Korai data, you were able to get the magnetic field from the calcium K brightness. I wonder that how the convolutional neural network get the sign right. I can understand within a cycle it can, but when the cycle change, would it get the polarity right?
A very good question. No, it can't. We don't think it can. There's a probability. We're trying to determine how to associate it. There's a probability. Any of these inferences, there's only a probability for getting the sign correct. And you're exactly right. Even in these, I think there are a lot of, you can't see it here because it's all like, it's very zoomed out, but there are many errors, I'm sure, in the field here. And you can't get that type of information. It simply doesn't have that information. So the machine is inventing some information based on some of the data that it's seen. It knows that if you have this type of field, then you have this type of polarity and stuff. Sometimes it's correct, sometimes it's not. So there are errors in that for sure. So you have to be careful when you interpret the field sign.
Thank you. That's it.
Just one last
The question is asked by Jayant. It is the second question of Jayant. I say about the same question. Thanks, Shravan. It's an excellent talk.
Thank you.
Okay, so thank you, Shravan, again for the very interesting. We now move on to the presentation of the award. Professor Peraiah Foundation Award 2021 is conferred on Professor Shravan Hanasoge from TIFR Mumbai for his outstanding contributions in the field of helio and astroseismology. I would humbly request Mrs. Peraiah to present the cash prize of rupees 1 lakh only to Professor Shravan. You have to go there. Okay, I now request
Share and
share.
no, it displays not there. It's shared.
Yes, you have shared it, right? That's just really- So he unshared it, I think. Sharing. the phone.
It's okay, I guess.
Yeah, it's fine.
So I now request our director, Professor Annapurni Subramaniam, to present a bouquet to the awardee. I also request her to present the certificate and the citation to the awardee. The citation reads as Dr. Hanasoge has made outstanding contributions to the understanding of convection and rotation in the sun and stars. Using novel techniques of seismology, he inferred that motions associated with convection in the sun are more than 10 times smaller than expected, an influential result that has come to be termed as the convective conundrum. Hanasoge was a part of an important study, the first of its kind, to measure the details of rotational shear in distant stars that are similar to our sun, a result that aids our understanding of the relationship between convection and rotation in the sun and stars. Okay, so we would conclude this award ceremony now with the vote of thanks. I'm grateful to our director, Professor Annapurni Subramaniam, for asking me to coordinate this award ceremony and for providing timely support and suggestions. And I also thank her for welcome address and for introducing the speaker. I would like to thank our Dean, Professor Ishwar Reddy, for his help and suggestions in planning today's program and facilitating an effective interaction between Professor Shravan, our academic faculty, and the foundation. I'm also thankful to Professor K. Rangarajan for being the foundation's point of contact. I would like to thank the Director's Secretariat, Mr. Manish Soni, and also Mr. Murali for their support in all matters relating to the award ceremony. I thank the Colloquium Committee for their help in announcing the award talk. I also thank Dr. Crispin Karthik for the live video streaming, Mr. Yogesh for proper deployment of audio-visual equipment and in helping with the photographs and bouquets. I also thank the IAA Scope committee for arranging the remote meeting. I thank the BGS office for providing logistical support for student interaction with the awardee. And thanks are due to the administration and canteen for food arrangements, Mr. Selva Kumar for the transport and accommodation arrangements, and computer support for the infrastructure. Professor Peraiah Foundation is a non-profit organization dedicated to promote and encourage research in theoretical astrophysics, in particular within India, and it has an MOU with IIA Bengaluru for organizing the award-related matters. Professor Peraiah Foundation has instituted this award with the objective to encourage scientific temper and excellence in research done in India. I would like to thank the foundation for continuing to promote and encourage astrophysics research in this in the field of theoretical astrophysics. And finally, I thank all the speakers and the awardee for an excellent talk. Lastly, I would also thank one and all present, either in person or remotely, for your active participation. Thank you.
Okay.